Good morning, Matthew students. Welcome to another fun-filled episode of Playing with Rational Numbers. So we're going to throw it back a little bit to, grade 6, grade 5, where you learned how to multiply and divide fractions for the very first time. We're going to remind ourselves how to do that, and then we're going to apply that knowledge to the more complicated fractions that we're dealing with now in grade 11, which is with all those funky fractional polynomials and perhaps even later on radicals and all that stuff, right? So it's the same concept, but with more complicated expressions, which is basically what we do for the rest of our life in math, is we reapply stuff we've learned previously in new situations and with more complicated looking stuff. So I'll just move my bon visage up here and we will get started. This is page 139 of your workbook. And we're just going to remind ourselves how we multiply fractions. Well, how do you multiply fractions? You multiply the topinators by each other, and you multiply the bottominators by each other. And when you do that, you get an expression that might look like this. And in fact, there's your answer. Now, there's no non-permitted values, of course, or non-permissible values, because there are no variables in here. And thus, there is nothing to restrict what the possible answers could be. These are the answers, easy as that. All right. Now, how do we deal with something like this? Well, it's the same thing, right? You go 6 times 14 and 7 times 9. Now, those are big, huge numbers, aren't they? I cannot multiply, well, I can multiply 6 by 14, it's 6 times 10, which is 60, plus 6 times 4, which is 24, 84, 6 times 14, 84. Magic. But you know what, there's a simpler way to do this, and that is by thinking about maybe doing a little bit of simplification before you do the multiplication. So you know that 3 goes in 6 twice, and if you look at the cross part of the fraction, 3 goes into 9 3 times. Likewise, 7 goes into 7 once, and 7 goes into 14 twice. So we could simplify this simply by now using your cross products and your cross factors. So 2 times 2 is 4 on the top, 1 times 3 is 3 on the bottom, 4/3. Okay? So it's a little bit of a simpler way to do it. You get the same answer, but why not help yourself if you possibly can? All right, so that's multiplication. Division of fractions is a little trickier, but not much. There is an old ditty that I learned in school back in the day, which goes something like, yours is not to reason why, just invert and multiply. And what we mean by that is that you take the first fraction, when you're dividing two fractions, you take the first fraction, you take the second fraction and invert it, that is, take the reciprocal. So 1 over 3 becomes 3 over 1, and you multiply them instead. But let's finish this off. 3 times 3 becomes 9, 4 times 1 becomes 4, and 9/4 becomes your answer. So in the last question in the box here, you got to ask yourself, well, how do I invert an integer? You turn it into a fraction, right? So 2 is really 2 over 1. And now you can do the inversion thing. And here it makes a little bit more sense. If you're dividing a number by 2, you're really multiplying it by 1/2. And that's exactly what's going to happen here. So 5/4 divided by 2 is going to become 5/4 times 1/2, right? Anything divided by 2 is that number multiplied by 1/2. And when you sort this out, 5 times 1 is 5, 4 times 2 is 8, 5/8 is your final incomplete answer down there. So this kind of thing isn't too hard. I mean, this is just a quick refresher, and if you don't remember how to multiply and divide fractions, learn it pretty quick now, okay? Because we're going to be throwing in those polynomials around and making these a little bit more complicated. Well, a lot more complicated in some cases. Explain why the non-permissible values of a given rational expression and its simplified form are the same. All right, so this has nothing to do with what we've done up there, but I want you to think about this. In the past examples, we had an expression which was a polynomial over a polynomial, and then we did some magic to it and simplified it. And when we looked for non-permissible values, we looked to both the denominators in the simplified form and in the original form. And I guess the question here asks, well, why? Well, here's why. You have to agree that the unsimplified form and the simplified form of an expression are the same value, right? They're equivalent. Well, if they're equivalent, then the non-permissible values of both have to come to play, have to work. All right? So, I mean, if you want to put that in words, we say, well, if they weren't, then the expressions would not be equivalent, would they? If the non-permissible values of both versions of the expression did not come into play, well, then we're not talking about equivalent expressions in the first place, and you haven't simplified properly, right? So once again, when you're looking at non-permissible values or restrictions, you have to look at both the original version and every single version in between. So if you go step, 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 okay, you have the non-permissible values apply to all different ways of expressing that expression. So, in general, when multiplying and dividing rational expressions, a over b times c over d equals a times c over b times d, where b and d may not equal to 0. Okay, that's your non-permissible values. And the difference between this and what we did up here is simply that there were no variables in these first examples, and now we're all of a sudden using variables, which is the complication now for Math 20-1. The first step in dividing a over b by c over d is to invert the second term and turn it into a multiplication, which will be a over b times d over c. Okay? And of course, when you finish this off, it's going to become AD over BC. And now your restrictions are going to be on B and C for sure, because neither B nor C may be equal to 0, because if it did, then the denominator would equal to 0, and the whole expression would become undefined. But neither may any of these denominators equal to 0. Now, B is already covered, because you see B here and you see D here. But we have the extra version of D here. So neither B nor C nor D may equal to 0. And that's because these two expressions here and here are equivalent. And you have to look for non-permissible values in both. So, as a step-by-step explanation of how to deal with multiplying and dividing rational numbers, factor stuff, state your NPVs, and simplify by divide. Now I would actually put this over here. I would factor, simplify, then look at your non-permissible values at both the original expression and its simplified expression. All right, let's do some examples. This comes from page 140 of your workbook. 23m squared n over 15 times 5mn over 8n squared. Now, there's a fair amount of simplifying you can do. You know, the 5s, for example, and the n squareds and the n's and so forth, right? But let's just bluster this all through here. What do we get? Well, if I want to start multiplying, it's a multiplication operation, so multiply the topinators and multiply the bottominators, and let's see what we get. So we're going to get 23 times 5 times n m cubed n squared. N squared because of this n times this n. All divided by 15 times 8 n squared. So that's our first. We're just laying out here the operations, okay? Easy to see all the bits here. So now we can do some simplification and some dividing out, right? You can do the dividing out in here if you want. You can do some slashes and then crossing outs, okay? But it might be easier here. So take a look. See the n squareds here and the n squareds there? They divide out to 1, all right? See the 5? 5 divided by 5 is 1, so there's an imaginary 1 there. 15 divided by 5 is 3, all right? So we can simplify that a little bit as well. So what are we going to get out of this all? Well, we've got 23 m cubed, all divided, and then we've taken care of the numerators, times, well, 3 times 8 is 24, and, well, no, that's it, just 24. So let me just write that a little bit more evenly there. There we go. There's our simplified expression. Non-permissible values, well, there's nothing here that I'm worried about, but there is an n over here. Now, the only restriction on the value of n is that n may not equal to 0, because if n equals 0, then this becomes 0 here. 0 times a number would still be 0, and your whole equation would become undefined. So n may not be equal to 0. Well, what about m? Anything? Well, it's not a restriction as such, but it's an expression of what m can be. M can be a member, can be anything. M is a member of the real numbers. If you have more than one variable in an expression, you will state the limitations or the restrictions on one of those variables, or both of them if there are restrictions on both. And if there are no restrictions on them, you should explicitly state that by telling us that it can be a member of the real numbers. It can be any value you want. All right. This looks both complicated but also strangely doable, doesn't it? Because you see some stuff that you recognize for sure. There's a trinomial times a binomial on the top, and you can expand that. You throw the x's through and throw the 7's through, 7 times everything and x times everything. And on the bottom, well, here, this might look a little familiar to you. You may want to do this. You may think that this is the first step to do. You may want to just expand out the x plus 7 times by multiplying x times every term plus 7 times every term. Well, if you do that, what are you going to get? You're going to get 2x to the 4th plus 10x cubed. See what I'm doing? I'm going like this, right? Plus 12x squared. Now I'll distribute the 7 across. Plus 14x cubed plus 70x squared plus 7 times 12, 7 times 10, plus another 14, 84x. All right? And, I could do the same thing down here by, well, let's do it. What the heck? X squared times 2x squared is 2x to the 4th plus 14x cubed minus 9 times 2 would be 18x to the 4th minus 9 times 14, well, 10 times 14, 140 minus 14, which is what, 126x. So that might be what you think would be a good start to this. And I think if you look at it, you'll agree that, man, that just looks messy and tough and difficult. You could probably work it through, but I don't see that easy way. So I'm going to ignore this, okay? I'm going to say, don't do it that way. That's a lot of work, and it may work out. I don't know. I don't have the patience, frankly. Let's see if there's another way. Well, there is. And that other way has to do with doing your factoring before you do your multiplying. What do I mean by that? Well, if you take a look at the 2x cubed plus 10x squared plus 12x, there's a common factor of 2x. So I'm going to pull the 2x out, and I'll be left with x squared plus 5x plus 6 times, of course, x plus 7. Okay, that's the numerators multiplied by each other. And on the bottom, again, you probably see a common factor of 2x. So I'll pull a 2x out, and I'll be left with x plus 7. And I'm hoping you're going to notice and identify x squared minus 9 as being a difference of squares. You know what that is, right? X plus 3 times x minus 3. Okay. All right. So we've done a little bit of factoring ahead of time now. And look what you can do. There's a 2x on the top and a 2x on the bottom. Those divide out nicely. Now they don't disappear. This becomes a big fat 1 in front of the whole expression. And 1 times anything is just anything. So I guess they do disappear, don't they? Likewise, do you see the x plus 7 and the x plus 7? Cool, I do. And now you do. There's a little bit more factoring you can do here. So let's take a look at factoring of the x squared plus 5x plus 6. I'm hoping you'll see that that can be simplified as x plus 2 times x plus 3. Does that work? X times x, there's your x squared, plus 3x plus 2x, there's your 5x, plus 6. Good. We've gotten rid of the x plus 6, x plus 7 over here, so we can ignore that because those have disappeared. Now on the bottom, I've got x plus 3 times x minus 3. Do you see a little bit more dividing out, or let's tick off the math gods and say cancel out. See a little bit more canceling out you can do? Sure. Here and here. Yeah? All right. So what am I going to be left with? Well, it looks like I only have an x plus 2 on the top and an x minus 3 on the bottom. And that, my friends, is a lot simpler looking than this, the original expression. And as I said, you could probably get to here by doing all this expansion, but I suggest you don't. I suggest you look at the factoring first. Well, it's not a suggestion, it's the way we do it. We always look to making our lives easier first, and that happens by doing your factoring. Let's look at non-permissible values. Well, there's a whole bunch of them, aren't there? Okay, so let's start in here. X may not equal to positive 3. Okay? If it were equal to positive 3, 3 minus 3 would be 0 in the denominator. Boom, it would not work. But this is an equivalent expression as well. And there's the x minus 3, but there's also an x plus 3 here, which means that x must not equal to negative 3 either, because in this form of the expression, which is the same as this, it's equivalent, right? Negative 3 plus 3 would also be 0, and so that would be not permitted as well. Phew. All right, are we done? No, we're not. We have to look at every single expression, moving all the way up here. So we've done with it. Let's take a look at here. There's the 3's, and now we have a 7 here. Do you see how x may not equal to negative 7? Because if x were equal to negative 7, this whole thing would be 0. 0 times this times this times this is still 0. So x must not be equal to negative 7 either. Oh, good, done. No, they're not. We've dealt with this expression, this expression. We have to go now and look at the original expression up here. Is there any limitation on x over here? What if x were 0? 0 minus 9 would be negative 9. Okay, no, that's fine. We're good. What if x were 0 here? 2 times 0 is 0 plus another 0 is 0. 0 times negative 9 would be 0. So because of this, x may not equal to 0 either. So we have, count them, 3 non-permissible values in this expression. Wow. All right, moving right along here. Here's the division question. Well, the first step you need to do when looking at a division question is to rearrange the expression as a multiplication, right? So x plus 7 divided by x squared minus 9 divided by that mess is going to be the same as x plus 7 over x squared minus 9 times 3x squared minus 9x over x squared plus 9x plus 14. Okay, so you've just done the inversion of the second term and then change the operation to a multiplication operation. We're good to go. Resist the urge to expand the polynomials. It will only lead to ruination and sorrow. Let's look at factoring first. Let's see if there's any factoring we can do. So on the top, I'm going to have x plus 7. Good. I can pull out a 3x out of 3x squared minus 9x. So there's my 3x term. And if I pull a 3x out of here, I'm going to be left with x minus 3, just like that. So I've simplified and factored out everything I could in the numerator. X squared minus 9, there's our good friend, the difference of squares. So x squared minus 9 is the same as x plus 3 times x minus 3. And x squared plus 9x plus 14 is a fairly simple case 1 trinomial, which means I've got two things like that to go on, right? And what are they? Well, I need a sum of 14, so I think 2 and 7 ought to work. Am I right? There's my x squared. There's my 7x, and a 2x makes 9x. Good. And then 2 times 7 is 14. Good. Cool. Well, what next? Well, I've got x minus 3 here and 3, so those can divide out. I've got an x plus 7 and an x plus 7. Those will divide out. I will be left with, looks like 3x on the top, and on the bottom, x plus 3 times x plus 2, just like that. There is my simplified expression. It's kind of weird, eh? Something this complicated gives the same exact values for all values you can put into x as this. Well, that's the beauty of simplification. It just works. All right, let's look at non-permitted values. Well, there's a whole bunch. There's going to be -3 and -2 here. So let's just keep a tally here, okay? Can't be x cannot be -3 or -2 because of this. Up here, it can't be +3 or, oh, looks like this -7. Good. And up here, no, there's nothing here, but we're missing one from here. What if x were 0? If x were 0, then this all would be 0 as well. So let's see if we got them all. Plus or minus 3, okay. 7 because of this. 2 because of this. And 0. So this is just an informal way of keeping track of all the things that x cannot be. So x formally may not be equal to. And to do this properly, you should probably go from the smallest value to the largest. So -7 would come first. Plus or minus, positive or -3 would come next. -2 and 0. There are all of your non-permitted values for x. All right. One last example here, and I don't know. It looks tricky, don't it? But it's not. You just take it step by step. Take it step by step. Because you've got some multiplication going on here and some multiplication going on here. Blah. Where to go? Well, let's take a look at this part first. Remember, when you're multiplying and dividing, it doesn't matter what order you multiply or divide by. So I can go this divided by this times this, Or I can multiply this by this and then divide it by this times this, right? But I'm going to deal with the first part of the expression this way. I'm going to go, I'm going to do this division here, all right? So 3x plus 12 over 3x squared minus 5x minus 12 divided by this bit here is going to be like times the inverse of 12 over 3x plus 4. So I'm going to put 3x plus 4 on the top and 12 on the bottom. So I've converted this into a multiplication. And now I'm just going to continue the multiplication by multiplying it by 2x minus 6 over x plus 4. Boom, just like that. So I've turned something messy into something a little bit less messy by converting the first division into a multiplication. So this whole circled bit here is what you see to the left of my fingers. And then I just added on the last multiplication. So now it becomes just a multiply through. But really, and this is the hint, this is the technique you use here, you don't just multiply through. You can, but you don't. Start doing your factoring and your simplification. So what do I got here? I can pull a 3 out of here. I can, well, there's not much I can do with the 3x plus 4, so I have to keep it. And I can pull a 2 out of the x plus 3, so 2x minus 3, okay? So I've pulled the 2 out of here, so there you go. I've simplified and factored as much as I can in the top. In the bottom, 3x squared minus 5x minus 12, well, again, it's one of those complex trinomials, right? I know that there is, I know it's this, right? And I know there's going to be a 3x and an x. And because I've got a 12 here, I now got to put a 3 and a 4. So it's a matter of, where does the 3 and where does the 4 go? So I know just a little bit of trial and error perhaps, but I know that works. Let's just double check. 3x times x is 3x squared. 3x times negative, so there's negative 9x plus 4x would be negative 5x, good. And then 4 times negative 3 is negative 12, good. So this is the proper factorization of that. Times 12, nothing we can do there, times x plus 4. Cool. Because now look what we got. There's an x plus 4 and an x plus 4. Boom, gone. Now here's a 3 times 2. That's 6, right? And there is a 12 here. So I can boom, boom, boom. I got 6 over 12 is the same as 1. I'm going to put the replacement of this over here. So I'm replacing 6 over 12 as 1 over 2. There's a 2. Good. Here's a couple negative 3's, x minus 3's that I can divide out. And there is even a 3x plus 4. Look, I can even divide that out. So I have been able to divide out every single variable term, which is kind of cool. Look, everything's divided out. Everything is divided out. I'm just left with that answer right there. So this whole mess right here equals a half. Wow. But it doesn't always equal to a half. There are certain values for x which make the whole expression undefined or indeterminate. So we've got to find out what those non-permissible values are. There are a whole bunch. I'm going to just make a list here. I'm going to go step by step through and we're going to figure out what those are. Well, let's just look at all the x values here. 3x plus 4. If this was 0, then everything else would be 0. So 3x plus 4 may not equal to 0. In other words, x must not be equal to negative 4/3 because of this 3x plus 4 term. What else? Well, x may not equal to 3 because of this. If x was equal to 3, then that would be 0. Nor may x equal to -4 because of this. All right? So there's 1, 2, 3 values of x which do not work because of this. And because this is the same as this, it doesn't look like there are any new restrictions in this expression of the term. There's the x plus 4, there's the x plus 4, so no change there. And there's an x plus 4, no change there. There's the 3x plus 4, no change there. And there is, so there we go. We found our non-permissible values. There's 3 of them. We will square the answer, but this answer is only the answer as long as x is not equal to -4/3, -4, or 3. We are done. Yay! Complicated, seemingly complicated, but they're always set up to make it look much simpler once you do the process, once you do your common factors, once you simplify and do your eliminations due to canceling out. Oh no, he said canceling out. Due to dividing out, you are good to go. Go forth, conquer these multiplications and divisions. Boom.